Welcome to the Matrix, our robot idea for the course Embedded Systems. The assignment is to create a robot that does something with black and white disks. This is, as you probably noticed, a bit of a vague problem. Our solution, a robot which takes a Boolean matrix and creates a visualization for it. The visualization will be created by storing the disks on a sort of slide where the top side of the disk is visible. And then a white disk is represents a 1 and a black disk represents a 0. First, to achieve this, we will need to detect a disk. We'll detect a disk when it is on the factory conveyor belt by shining a light across the conveyor belt. If the light beam gets interrupted, we'll know there is a disk there. Then we'll detect the color of the disk in a somewhat similar manner. We'll shine a light on top of the disk and then measure the amount of reflected light. A white disk will reflect more light than a black disk. Now, as soon as we've detected the disk, we'll ask for permission to take it from the main server. As soon as we get that permission, we'll push the disk onto our own conveyor belt. Then we'll determine in what column of the matrix it should go, and we'll push it into the right column. Now, this all sounds well and good, but there are a lot of opportunities for things to go wrong, and so we need a way of detecting errors. There are three main types of errors. Mechanical malfunctionings, such as motors getting stuck or blocked conveyor belts and stuff like that. And we'll detect these kinds of errors using limit switches and timeouts. So when a moving part wants to move from one position to the other, we'll put limit switches at both positions, and we'll measure the time it takes to move from the one to the other position. Now, if it takes much more time than that, we'll know something has gone wrong, and we can detect the error. The second type of error is irregularities with transporting disks. Disk can fall off the conveyor belt quite easily, so we'll need to add railings to prevent that. And now, even though we will add railings, something can still go wrong. So we will add a few of the same mechanisms we use for detecting disks in the first place alongside all of the conveyor belts to ensure that we will detect if disks still get lost somehow. And the final error is loose wiring or dysfunctional sensors. So when a wire is pulled loose, we will read random values, and when a sensor is dysfunctional, we'll also read weird values. So we can detect those by measuring what a normal input, what the range of the normal inputs is, and as soon as we detect something other than that, we'll know something has gone wrong and we can alert the user. Now, detecting errors is very important, but not having errors is even better. We will use model-based design to ensure the most error-free code and hardware we can get. We already have a static 3D model, which we use to visualize multiple prototype designs, but we also need a non-static model. We'll use the strength that our team already has instead of learning new modeling tools, so we'll write our own emulator, which mimics the real world. This will be a program that simulates the inputs of our main program and then takes the output of the main program as inputs to update its simulation, and with that way we'll be able to test if the main program behaves as it should behave. Now finally, we have come to the actual implementation. We will program the robot using Java. We all have most experience in Java programming, much more over, for instance, Python, which is widely used for the Raspberry Pi. Python might be more used, but the Java offers a few libraries that we can use to control the hardware directly. We have chosen the Java DO library as it can be used with the normal Java SE and is simpler in use than other options we considered. For the hardware side of the project, we already have built the first prototype. We have a hand-driven factory conveyor belt with light and color sensors over. an arm that pushes the discs from the factory conveyor belt onto our own conveyor belt, and then finally a slider which pushes the discs into the right columns to visualize the matrix. Now, I hope this presentation has given you enough insight into the design of our robot and how we will incorporate both error detection and model-based design into the creation of said robot. If there are any remarks or questions, please let us know. We'll be glad to answer those. Thank you very much.